Okay, seems like everyone is ready, including our speaker. It's now the time of Charlie Beil. He will speaking about diamond models. Is the third lecture. Please, Charlie, go ahead.
Okay, so today we will pick up where we left off yesterday, and that was the question of non-Noetherian geometry, because the centers of these algebras are usually non-Noetherian. Okay, so the question that we first ask is, what is the geometry of a non-Noetherian integral domain K algebra? So what does the maximal ideal spectrum or the variety for R look like when R is non-Noetherian? And the first answer, of course, you would say it's a non-Noetherian scheme, but there's no concrete geometric picture associated with this, and so we want something we could, that's more geometric, that one could visualize. Okay, so to start, we have let S be the polynomial ring in two variables and consider the non-Noetherian subalgebra R, which is K plus the ideal generated by X and S. So this is a non-Noetherian ring, and we can ask, what does the algebraic variety of max R look like? And a more complicated example, so let S be the polynomial ring in three variables and consider the subalgebra R, which is K adjoin X squared minus Y minus Z squared, plus this complicated looking ideal, X squared minus Y and Z minus 5 times X minus Z, comma Y. So this messy, complicated looking ring, we could also ask, well, so first, is this ring non-Noetherian, and what does the algebraic variety for R look like? So first definition we give is that of a depiction, and so this is an integral domain K algebra R, which is a finitely generated a depiction of an integral domain K algebra R is a finitely generated overring S, such that the morphism from spec S to spec R, where you just take a prime ideal of S and you intersect it with R, is surjective. And we'll call this morphism iota. And this locus U, so this is sitting inside of the algebraic variety for S. So again, S is just, you could think of as a coordinate ring. So this locus U is the point where, when we localize at that point, it's equal to R localized at that point. So R localized at N intersect R, where N is a maximal ideal of S. And we want this to equal the points N in max S, so the maximal ideals of S, where R localized at N intersect R is Noetherian. And we want this to be non-empty, this set to be non-empty. So this is a depiction. This is kind of the main tool that we'll use. The geometric height of a prime ideal of R is the minimum of the heights of the prime ideals of S, where S ranges over depictions of R, of ideals Q, where Q is in the preimage of P, where the preimage is with this map given above, this iota of S over R. Okay, so this is the geometric height of this prime ideal P, is just given by this minimum of heights of prime ideals Q, sitting over P, where we look over all the depictions of R. And the geometric dimension of P is the Quirrell dimension of R minus this geometric height. So it's something replacing the height of an ideal, but yeah, it will be useful. In our first example, where we have S as a polynomial ring in two variables, S is a depiction of the ring R, which is K plus X times S, and the y-axis, so where X is non-zero, the locus X is where X is non-zero, so the complement of the y-axis is the Noetherian locus, U. And we thus view max R as the variety max S, which is just two-dimensional affine space, except that the line x equals 0 is identified as a one-dimensional closed point of max R. So the y-axis is this single kind of one-dimensional point. There's no interior points in it. And outside of the y-axis, everything looks just as two-dimensional affine space. So we can actually visualize what this ring R looks like. The variety for this ring is just we have this one-dimensional point. But other than that, it just is completely just something, yeah, very concrete that you can visualize. Okay, so the first theorem is that if S is a depiction of R, then the Quirrell dimension of R equals the Quirrell dimension of S. So even though R is non-Noetherian, it still satisfies the ascending chain condition for prime ideals. And furthermore, the Noetherian locus U is an open-dense subset of max S, and thus max R and max S, these two varieties, are birationally equivalent. Okay, the second theorem with this is that we can ask, okay, now we have, if there's just one of these positive dimensional points, we just have K plus this ideal for that subvariety. What if we have more than one point, positive dimensional point? Can we make this work? And so let X be an affine algebraic variety over K with coordinate ring S, and consider a collection of pairwise non-intersecting algebraic sets y1 through yn of X, where each ideal of the yi's is a proper non-zero and non-maximal ideal. Then the maximal spectrum of the ring given by the intersection of K plus the ideal for each yi. So we take the intersection of these K plus these ideals. This will coincide with X, except that each yi is identified as a distinct closed point. In particular, the locus U sitting inside of X is given by the intersection of the complements of all of these yi's. And furthermore, we have that R is non-Noetherian if and only if there is some I for which the dimension of this subvariety yi is strictly positive, and R is depicted by S if and only if for each I the dimension of each of the yi's is strictly positive. Sorry, greater than or equal to 1. Okay, so recall our second example. Let S be the polynomial ring in 3 variables, and consider the subalgebra K adjoin x squared minus y minus z squared plus this messy looking ideal. Well, we can rewrite this as an intersection of K plus an ideal intersected with K plus another ideal. And so here's our 2 ideals right here. And by the theorem, max R looks exactly like 3-dimensional affine space, except that these 2 curves, the zero locus of these two curves. So x squared minus y intersect with z minus 5. So we get a curve there, and x minus z intersected with the locus for y equals 0. These are each identified as a one-dimensional point. So this crazy looking ring actually has a perfectly visualizable picture to associate with it. And it's just three-dimensional affine space with these two curves that are each single one-dimensional points. But there's nothing, mysterious about it. It's just, you just have to allow there to be these positive dimensional points. So basically subvarieties that are positive dimensional, but with no interior points in them. So furthermore, R is non-Noetherian and depicted by S, and the complement of the two curves is the Noetherian locus U. Okay, now we go to the question of unique maximal depictions. So in general, maximal depictions need not be unique. So consider the rings S, which is a polynomial ring in 3 variables, and R, which is k plus xy times S. Then these two overrings, S adjoined x inverse and S adjoined y inverse, are both depictions of R, whereas their minimal proper overring, S adjoined x inverse and y inverse, is not. So then we can ask the question, what algebras admit depictions? And this will all play a role with the Gore algebras later, in the dimer algebras. Okay, so we give a definition. We say R is Noetherian in codimension 1 if R admits a depiction S such that each codimension 1 subvariety of max S intersects the Noetherian locus, this open dense set U. And this definition of Noetherian in codimension 1 is independent of the choice of depiction. So you can, if R is Noetherian in codimension 1, it looks like it depends on the ring S, but it does not depend on the ring S. And if R is Noetherian in codimension 1, then for each height 1 prime Q in S, the localization R localized at Q intersect R is Noetherian. Okay, so now we have our last theorem in this section. And so suppose R is Noetherian in codimension 1. Let S be any depiction of R, and consider the global sections ring, which is the global sections on this Noetherian locus. So this is just the intersection of all these local rings of S localized at the maximal ideals in this Noetherian locus. So in other words, it's the global sections on the set U. So T is the unique maximal depiction of R, and in particular, T is independent of the choice of depiction. So it looks like T depends on S, but it does not. And for each prime P in spec R, there is some prime ideal T in T lying over P such that the geometric dimension of P equals a Crawl dimension of the quotient of the ring T modulo this prime ideal. And let S be the normalization, S bar be the normalization of S. Then S sits inside of T, which sits inside the normalization of S. So we'll use this result when we talk about dimer and Gore algebras. And in particular, S so if S is normal, then S is the unique maximal depiction of R as well as the unique normal depiction of R. So again, we'll use this that if the depiction is normal, then it's the unique maximal depiction of the ring, R. Okay, so now we review again what were Daimer and Gore algebras. And just to recall from yesterday and Monday, a Daimer quiver on a surface sigma is a quiver Q whose underlying graph, Q bar, embeds in sigma such that each connected component of the surface minus the graph is simply connected and bounded by an oriented cycle called a unit cycle. And so in the picture here, all these little cycles were the unit cycles. And the Daimer algebra of Q was the quotient of the path algebra modulo the ideal I generated by differences of paths P and Q, such that there exists an arrow A where PA and QA are unit cycles. And this one that we looked at before on this octagon is we identify the opposite sides, and so it's sitting on a genus 2 surface. And we'll actually today, hopefully if we get there today, we'll write the center of this algebra down explicitly, and it all depends on the perfect matchings and things like this. But we'll come back to this example and look at it in a real concrete way later today or Friday. Okay, and a perfect matching, again, this is the same definition of a perfect matching from bipartite graphs and surfaces or Playbit graphs, things like this. We're just using the dual quiver in the bipartite graph. So when you are on the dual quiver, a perfect matching of a Daimer quiver is a set of arrows X in Q1. Q1 is the arrows, such that each unit cycle contains precisely one arrow in X. And the perfect matching X is called simple if the quiver minus, if you omit the arrows in our perfect matching, you can still have a cycle that passes through each vertex of Q. And it's called simple because it supports a simple module of dimension vector all ones. And we denote by script P and script S the set of perfect and simple matchings of Q, respectively. Okay, now we'll recall the definition of a Gore algebra. So consider the polynomial ring generated by the perfect matchings of Q, and label each arrow of A of Q by a monomial. And today I'll use eta bar. On Monday, I just put a bar here, so I use both notation, but this is, the others are more shorthand notation. So eta bar of A is a monomial in this polynomial ring generated by the perfect matchings, where we have, if A is contained in the perfect matching, the arrow A, then X will be part of this monomial that's corresponding to A. So each arrow gets a monomial, and the monomial has a variable for each perfect matching that it's contained in. So hopefully this is okay. But yeah, so the monomial, you have a variable for each perfect matching, and there's a variable is part of the monomial for some arrow if that arrow is contained in the corresponding perfect matching. So then we just extend this multiplicatively to all paths. So you can take a path P, which is a product of A1, A2 through AL, where these are arrows, and then we just multiply all these monomials together on each of the arrows to get the monomial for the path. So the way you can think of this is just you're writing monomials for each arrow in the quiver, and the monomial is telling you what perfect matchings that arrow is contained in. And we define the Gore algebra of Q just to be we identify two paths if they have the same monomial labeling. Of course, we want the paths to have the same starting vertex and the same ending vertex. But if you take two paths with the same starting vertex and ending vertex, and they have the same monomial labeling, then we want to identify these two paths and say these are the same, and so this is what the Gore algebra is. So again, the relations are coming from the perfect matchings. Is defined, entirely from the perfect matchings. Okay, and recall that for a path P, we have the eta of P. So this was a matrix without the bar over it. So if we just have eta of P, this was a matrix, and it just has one monomial times this matrix with a 1 in one slot and zeros everywhere else. So we looked at the concrete example of this map eta yesterday with the conifold quiver. And so it just sits in this matrix ring over this polynomial algebra generated by the perfect matchings. So the thing that we'll get to today is that we don't, in the cases that we'll be looking at, we don't need all the perfect matchings, and there can be many, many perfect matchings, but we just need the simple ones. So in the cases that we'll be looking at today, we can ignore all the non-simple perfect matchings and just look at the simple ones. And so this tau bar here of a path, you just take the monomial and you just set all the variables that are not simple matchings equal to 1. And all the rest of the variables that are simple matchings, you leave them alone. But the ones that are not simple perfect matchings, you set these variables equal to 1. And so this is this tau bar here. And these monomial labelings define k-linear maps on A and lambda for each pair of vertices. So A, again, I use A for the dimer algebra, lambda for the Gore algebra. And so here we have, from each of these corner rings, EI, A, EJ, we have a k-linear map. So eta bar takes you to this polynomial ring generated by the perfect matchings, and tau bar takes you to the polynomial ring generated by the simple matchings. If I is equal to j, then this is also an algebra homomorphism. But when I is not equal to j, we can't, of course, have an algebra homomorphism, so it's just a k-linear map. Okay, so now we ask, what is the central geometry of non-Noetherian dimer and Gore algebras on a torus? So by central geometry, I mean, we have these algebras, we look at the centers, and we want to say, what's the geometry of the center of these algebras? And so just things to recall from Monday is that, so again, we're starting with just the torus case. A dimer algebra is Noetherian if and only if it is cancelative. And the Gore algebra of Q is the quotient of A by the non-cancelative pairs of paths. So if you remember these definitions from Monday. And a dimer or Gore algebra is Noetherian if and only if its center is Noetherian. And cancelative was just, you can, if PR equals QR, you can cancel the R and say P equals Q. So this was cancelative. And the R can go on the left or right side. So PR equals PQ, or RP equals RQ. Okay, and then also we looked at these non-cancelative dimer algebras on a torus on Monday. So the arrows in red do not annihilate any simple A module of dimension vector all at once. Or equivalently, they are not contained in any simple matching. So that's what it means to not being a simple matching. So we looked at these algebras on Monday, and now we'll look at them some more today. So what happens if we contract the arrow, these red arrows to vertices? So we take these red arrows and we contract them to vertices. Well, if we do the first one, if we contract both of the red arrows, we have a problem because then it's no longer a dimer algebra on a torus. So we just contract one. And if we just contract this one red arrow here, we'll have psi as our map from, yeah, it'll end up being the map we're looking at. We contract this red arrow, we get the conifold. So this is the one we spent yesterday looking at for a long time. And okay, the next one, if we contract the red arrow on the next one, well, we get this right here. But we have these two cycles, but the two cycles these arrows are just redundant generators for the algebra, because by the dimer algebra relations, if you take this arrow here, that's the same as going along this path and this path, because we have an arrow there. So we can remove these two arrows in the two cycle because they're redundant generators for the algebra. This is why we require there be at least one perfect matching in the quiver, because if you don't have that condition, it's possible you have two cycles that you can't remove. Okay, so when we remove these two cycles, so these redundant generators in the algebra, we end up again with the conifold quiver. So see, these are the same. This again is the one we looked at for a long time yesterday. And then we'll take the third one. If we contract this arrow, this red arrow that's not contained in any simple matching, and again, it's the only arrow in the quiver that's not contained in any simple matching. All the other ones are. Again, same with this one too. This one had these two arrows, but these ones, this is the only arrow here and not in the simple matching, and same here. So we contract this red arrow, we get a two cycle, we remove it, and we get this. Okay. So the first two are just the conifold dimer algebras, which is Noetherian. The third dimer algebra, so this one here, is also Noetherian because you can check it by seeing that each arrow is contained in a simple matching, or equivalently, the quiver admits an isoradial embedding, which you can see by just putting a circle around each unit cycle that has the same radius. Since we can do that, we know it's going to be Noetherian. And so what we've done is we've contracted this red arrow, and once we've done that, we have Noetherian dimer algebras. So yeah, we get Noetherian dimer algebras. Okay, in these examples, is there any relationship between the center of the non-Noetherian dimer algebra and the Noetherian one it contracts to? So to answer this, we first need to formalize what we mean by contraction, because we can't, of course, contract whatever arrows we want, because then say we can, contract everything down to just one vertex. So we need to have some structure that's preserved. Okay, so let A be a dimer algebra, and suppose a Noetherian dimer algebra A prime is obtained by contracting a set of arrows of Q. So Q goes with A, Q prime goes with A prime. If the relations are preserved, then we obtain a k-linear map psi from A to A prime. If so, this is the first thing is we first want the relations to be preserved. And so this was an example here that we had just looked at. We contract this red arrow and we get this. And so we end up with this Noetherian dimer algebra. And if psi preserves the cycles of Q in the sense that the algebra, K algebra generated by the union over all the vertices of the, here's our tau bar, the tau bar psi images of each of these vertex corner rings, EI, AEI, is equal to the union, so the K algebra generated by the union over all the vertices of Q prime, so this guy, of tau bar, the tau bar images of EI, A prime, EI. So now we're over here. So here we have our psi is right there. And so we take cycles over here. We look at their images over here in Q prime. And we look at the, so this tau prime is the simple matchings, the monomials from the simple matchings of Q prime, not of Q, just of Q prime. And if we have this equality between these two rings, then psi is called a cyclic contraction, and we call S the cycle algebra of A. So this will be our main tool to study the non-Noetherian dimer algebras on a torus. And it's a way of, we contract arrows, but we preserve this, basically we're preserving the cycles in the quiver. Even though we're contracting arrows, we're preserving the cycles. Okay, so the first is, you can ask, do you always have these cyclic contractions? And the answer is yes. As long as you have at least one perfect matching in your quiver, cyclic contractions always exist for dimer algebras on a torus. And the cycle algebra, in addition, the cycle algebra S is independent of the choice of psi, even though we defined it using S, using psi, the contraction psi, the cycle algebra is independent of that choice. Okay, so now let psi be a cyclic contraction from A to A prime. And recall that A prime is equal to lambda prime. So the dimer algebra and the Gore algebra with the same quiver are equal since A prime is Noetherian. So what this means is we can replace the A and A prime in this condition that we just had above with lambda and lambda prime. Because, so lambda prime, the Gore algebra of the quiver Q prime is equal to A prime. So we can just put in the lambda prime there, and then it's not hard to see, you can put in, instead of the A here for the non-Noetherian algebra, you could put in lambda, so this is our non-Noetherian Gore algebra. And the psi also defines a cyclic contraction of Gore algebras. So you can have these be A and A prime here, or lambda and lambda prime. And either way, it's okay. And these are the same in any case. The cycle algebra will be the same, using either the dimer algebra or the Gore algebra. Okay, so now let psi be a cyclic contraction of Gore algebras from lambda to lambda prime. And recall the cycle algebra. So here it's the algebra generated by the union over all the vertices of Q naught of the tau bar psi images of these vertex corner rings, EI, lambda EI, and set R to be the K algebra generated instead of by the union, now the intersection over all the vertices of these tau bar psi images. And so the theorem is that the centers of lambda and lambda prime are given by the intersection and union of the tau bar psi images of the vertex corner rings of lambda. So we have this condition here. So it's very nice kind of property that these have, is that we can have the center of lambda explicitly as R, this intersection, and the center of lambda prime is S, so the union. And S again is also the cycle algebra. Okay, so Okay, so this is back to our examples. We can see now we can write down explicitly what the cycle algebra and center of the Dimer or Gore algebras look like. Well, here we just say Gore algebra because this will not, in general, R will not be the center of the Dimer algebra, but we'll get to that in just a minute. Okay, so in the first case, S, so it's just the coordinate ring for the conifold, the quadrant cone that we looked at yesterday. So we had this XZ, YZ, XW, YW. So that's the center of this guy. So that's what we found yesterday. And this R, now notice it's K plus an ideal in S. So it's just exactly of the form that we looked at before with depictions. And in fact, we do the next one. We also find the same thing. Again, S is the conifold coordinate ring, which is the center of this guy. And R is K plus this ideal. So it's again K plus some ideal. And so these are non-Noetherian rings, which we already knew the centers were non-Noetherian, but here's what they are explicitly. And in our last case, it's just a more complicated cycle algebra S, so which is the center of this guy. And R is K plus an ideal in S. And the perfect matchings I'm using for the X, Y, Z, and W are just the same as yesterday. Okay, in each case, S is a depiction of R. Of course, you need to work this out and see that this is true, but this is the case. So the theorem is that let psi be a cyclic contraction from lambda to lambda prime, then the center S of lambda prime is the unique maximal depiction of the center R of lambda. So S is a depiction of R. We know that S is a normal ring because of the things done around 2010 with the cancelled Dimer algebras. And by the theorem, with the last theorem I stated in the depiction section, if you have a depiction that's normal, then it will be the unique maximal depiction of that ring. And so we know that S is actually kind of the nicest depiction there is for R. And the second thing is that the algebraic variety, or the variety for this non-Noetherian ring R, contains precisely one point of positive geometric dimension. So it looks just like a three-dimensional affine toric Weinstein singularity, which is what S is, except there's one positive dimensional subvariety, so either dimension 1 or 2, that it is identified as one single closed point. So consequently, the non-Noetherian scheme spec R is birational to a three-dimensional Noetherian affine scheme. So we see that depictions allow us to make sense of the geometry of R. We can have something that's perfectly a concrete geometric picture, even though the center is non-Noetherian. All is well. We just have positive dimensional points, and in this case, we know there's one unique positive dimensional point in the variety, and outside of this positive dimensional point, everything looks exactly like the Noetherian case. Okay, how is the center Z of A related to the center R of lambda? So that's the next question. So everything so far is just with the Gore algebras. So what about the Dimer algebras? Well, okay, this quiver here on the left is a non-cancellative Dimer algebra on a torus. And here on the right, we've I've drawn more than one fundamental domain. So this is kind of drawn in the universal cover of the quiver. And so consider the paths P, Q, and A drawn in purple, blue, and orange on this picture. Then the element P minus Q times A plus A times P minus Q is central, and it actually is squares to 0. So it's a nilpotent element of the center, which is crazy. This is actually why I kept going with dimer algebras when people in 2010, when people had found the things about the cancelled dimer algebras, and that was kind of done. This was very interesting to me that there's this other structure here with the non-cancellative ones. So therefore, the center of A has a non-zero nil radical. And yeah, so this was very surprising that this is a central element and it squares to 0. Okay, so denote by nil z the nil radical of z, and by z hat the reduced ring of z, so just z mod the nil radical. Then the theorem is let psi be a cyclic contraction. Then the nil radical is actually equal to the kernel of psi intersected with z. So this is, I think this is very nice how it works out with the cyclic contraction. And moreover, the reduced ring of z equals the center r of lambda. So we get r, but we just have to mod out by this nil radical. So everything I said before with depictions and the cycle algebra holds for dimer algebras on a torus that are non-cancellative. But we just need to mod the center out by the nil radical. Now, the nil radical is often 0. I think probably it is, yeah, I don't know if it's most cases or how to quantify that, but in many examples, it's 0, the nil radical is 0, so just z would equal r, but when it is non-zero, we mod out by it and we get r. And so consequently, z hat is an integral domain of curl dimension 3. And because R is an integral domain. And dim z, the curl dimension of z, is equal to the curl dimension of its reduced ring. And so that's equal to the dimension of R, which is 3. And we know this is 3 because it's depicted by S, and the curl dimension of S is 3. So we used depictions to get this here, what the curl dimension is. Okay, so now what is the central geometry of non-Noetherian dimer and Gore algebras on higher genus surfaces? So we did the torus case, and we want to look at higher genus cases. So the first thing to look at is fundamental. We talk about the topology of the surface, so fundamental polygons. So sigma here is a surface obtained that we'll look at. We'll focus on surfaces obtained from regular convex 2 n-gons, where n is at least 2, and we identify the opposite sides of P and all of the vertices of P. So exactly like what we've done in the examples I've shown before. So if P is a 4G-gon, then sigma is a smooth genus G surface. And these pictures are from Wikipedia, but here's a genus 1, a torus, genus 2, a genus 3 surface. And if P is a 2 times 2G plus 1 gon, then sigma is a genus G surface with a pinch point. And in either case, P is a fundamental polygon for sigma. So if n equals 2, sigma is a torus, and the covering space of sigma is just R2. However, if n is at least 3, then the covering space of sigma will be the hyperbolic plane. So here's a hyperbolic plane. The hyperbolic plane may be represented by the interior of a unit disk, where straight lines in H2 are segments of circles that meet the boundary of the disk orthogonally. So these are all straight lines in this two-dimensional hyperbolic space. These are parallel to these. Here's an MC Escher picture of hyperbolic space. And so here is an example. Here P is a hexagon. We can take, so remember we drew on the first day, I had a picture of a dimer in a hexagon where I identified the opposite sides, and it would really in the hyperbolic plane be drawn on this. So this would be the cover of the surface, and the surface is, oh, somewhere the picture went away. It's a pinch torus. The picture is not there, but yeah, you take a torus and you just pinch one part of it. So now it looks like I should stop here. So the next thing we'll talk about is Gore algebras on higher genus surfaces. So I've set up the kind of topological part, and then so on Friday I'll talk about this and cluster algebras. All right, thank you very much.
Thank you very much, Charlie, for this beautiful talk.